Hi, this is Yijia. So welcome to the 8th day Origo's Whitepaper Workshop. And today's content will be a little shorter. Today we are mainly focusing on Origo's virtual machine design. And the lost stuff is still under development and under design, so not everything is actually finalized. But I want to give you have an overview of the virtual machine design. As we yesterday mentioned about a virtual machine is most useful for smart contract because you need that kind of environment to actually execute the operations from this stack, from this state to another state, or from handling different kind of operation add, mod, bits manipulation, those kind of detailed stuff. And so basically this is a straightforward on this graph is like a developer write a smart contract, and this kind of smart contract will compile to a bytecode. And actually, the blockchain it doesn't store the smart contract directly. It actually store the bytecode. So which when the contract get called and goes to this address and then call to this function, you actually bring this bytecode to a virtual machine, and the virtual machine will execute the command like a line by line or actually operation one by one, and then modify the states. So that's the normally virtual machine. Pretty actually useful for smart contracts. So what's Origo's virtual machine for? Or what need to be changed? So firstly, we want to base on WebAssembly, so which will a broad used. And for example, like a Chrome browser can support a WebAssembly. So this is more like a lower level operations. We want this to as a baseline. Then it could actually support multiple programming languages input in the future. So you can have a multiple DSLs. So actually, you can support more language. But the basic virtual machine operations will have using WebAssembly will support more. So this is the basic design. But what's else for Origo? So for Origo, there's one thing a pretty different than Ethereum is we need to use zero knowledge proof to actually prove and verify the privacy preserving smart contract execution, and also the commit step to verify verify whether the you have the coin, and in the commitment step is in the open step you need to verify the content, whether matching the commitment, whether matching the encrypted stuff, and also there are other more logics. So we want this kind of a zero ZKP proof and verify logic can also be running in the same virtual machine. We don't want to hardcode those stuff. We want it to actually run in the same environment. Then we require the compiler and the VM integrated with a ZKP system. So for example, we want the virtual machine actually support those kind of ZKPs, verifies, or those kind of operations. So for privacy preserving smart contract, what is this for at the execution compiled to normal smart contract? So firstly, we use a zero knowledge proof. So for zero knowledge proof, we need to compile the program to arithmetic circuits. So you can think about it usually you compile a program to bytecode, and then you run the bytecode. Bytecode can downgrade to for assembly language. It's more like a machine operation one by one, right? But for a smart contract, for a zero knowledge proof stuff, it's more like you compile those kind of logic into arithmetic circuits. Yeah, those stuff will be you can find that in our white paper also talk about that, but you can find that in Wikipedia or other stuff talk more about the arithmetic circuits. So it's more like you can think it has the similar level before the bytecode, and so our virtual machine need to able to like run the circuits to produce the proof, and also our virtual machines like operation need to have the ability actually to verify these proofs. So in this way, we can actually support both like and also we need to like normally support other like operations for other public. So you have like a operation for zero knowledge proof, like verify and proofs, and also like operations for normal add, mod, and multiply those actions. So we need to support both like a public and the private preserving smart contracts. So it's more like based on the normal virtual machine, we need to add more functionalities other than operation or like operation functions other than normal virtual machines actually to support this. So and so we will base on UVM at first with extended opcode, so extended functions to actually support the ZKP proof and verify operations with the circuits which compiling from the program. And for private preserving, we will first limited the solidity functions with a strict on certain operations to achieve like better performance. You just think about like you compile like a really complicated stuff into a arithmetic circuit. Well, making the circuit actually larger, much larger. So you cannot say open all of the functions like directly to like all of the function, or all the ways you writing solidity at the same way you actually generating the circuits. And this is not efficient. So we are limited the solidity and with a strict on certain operations. So then it can actually we can have better design to support and then can achieve better performance. And also for other like for public contract, it's the same as normal EVMs with normal Ethereum. It doesn't need to have any limit. So this limit will only happen on private preserving. Is the reason for the limit reason is to achieve better performance. So that's the only reason we do that. So intend to like use solidity as Origo's DLCL. The reason we're using the solidity is because we want to minimum the effort required for like a migrating smart contract from Ethereum to Origo. So you don't need to actually learn another language. So which is good. So I don't want to say, okay, we design a new language and you need to learn again. We just want to say if we want to limit some limitation, we just tell you, okay, this function is using by this way will be faster, and this is the like a good practice to writing solidity to compile to circuits in private preserving environment. So then that'll be good for like a developers. So developers doesn't need to like learn a new language again to on Origo. This is not good. So we want to like we can have other DSL to support like other language. Like we can maybe support C++ or whatever other language with limitation. But we intend to use like solidity as first to minimize the migration effort for developer. So yeah, so this is the whole pipeline. So compare to the normal ones. So it's more like a developer write a smart contract, that's the same. And then for public, you compile the program to like a bytecode, and then you store the bytecode on the blockchain. For private, you may need to compile the smart contract to circuits, and then you store the circuits to blockchain. Well, actually, doesn't need. We can have other logic, other tricks. We still under design for how to handle the circuits, and so the virtual machine need to when it in the execute environment. For normal public, you just need to execute the bytecode and then change the state. That's done. And for private, the virtual machine need to have the ability to actually run the circuits and to generate the proof. That's in the execute state for private. And in the verification stage, the node's virtual machine, usually for public, you just need to run it again and run the same bytecode. But for private preserving state case, you need to verify those proofs and using this kind of circuits. And those stuff happen in the virtual machine, the same virtual machine. So it's more like we need to add more operation code to actually support this kind of circuit stuff and have better design to actually suit this environment. So that's the new stuff from Origo. We don't want to say this is like a totally new stuff. This is more like we just want to handle this circuit stuff better. And maybe increase the efficiency. And we have the plan, and we are still doing is like implement a better compiler for compiling those circuits to increase the usability. So like a developer doesn't need to know detail about the zero knowledge proof, but still can writing normal solidity, and then bang, things get done. It auto compile to circuits and auto verify. So we want to have this kind of tool chain to actually help the developer to scale the stuff. So thanks for listening for today's talk. And tomorrow I mentioned a lot to talk about a different trust model, and tomorrow I will talk about the trust model. And thanks.